Hi there. In this video, we're going to talk about even and odd functions in the context of Fourier series. So basically, it really helps to identify if the function that we're writing the Fourier series for is an even and odd function. Simply by just doing that, we can simplify a lot of our work. And just by judging that, we'll be able to say, okay, a Fourier series will contain only sine terms or only cosine terms or whatever it is the case. So let's just do a quick revision of what even and odd functions are. We can start off with even functions. So an even function is a function where if we substitute minus x into the function, we get f of x. So the simplest illustration of this is just to consider y is equal to x squared. So just a parabola. So we have a parabola, y is equal to x squared. So we can see that if we substitute minus x inside this, then we'll still get the same value. For example, if we say f of 2, or rather f of minus 2, then we're going to get minus 2 squared, which is 4. So we can see that regardless of whether it's x or minus x, we'll still get the same y value. So the moral of this story is that an even function is symmetrical about the y-axis. So if we put a mirror on the y-axis, whatever we will see on one side, we will see on the other side. So symmetrical about the y-axis. So since we're talking about Fourier series, we have to consider the trigonometric terms. So we can look at cos x. So if we just quickly draw the graph of cos x, so we have minus pi, pi over 2 and pi over 2 and pi. So we know that it starts off at 1 at minus pi, it goes to minus 0 at pi over 2, then it goes up to 0, and it carries on like that. Okay, this is drawn quite poorly, but I think you get the idea. So that's minus pi, that's pi over 2, or minus pi over 2. So that's 0, so that is pi over 2, and that's pi. So we can see that we get minus 1 at minus pi there, and we also get minus 1 at pi. Okay, so in other words, cos of minus x is equal to cos x. So this is a general trigonometric identity which many people will be aware of. So this means that it's an even function. It is symmetrical about the y-axis. So these are even functions. So let's look at odd functions. So for an odd function, what happens is f of minus x is equal to f of x. So the easiest illustration of that would be perhaps the graph y is equal to x cubed. So x cubed looks something like this. Okay. So this is f of x is equal to x cubed. So if we were to substitute minus 2 here, then we get minus 2 cubed, and we see that we get minus 8. So similarly, if you put in f of 2, then you'll see that you would get 8. So what this is saying is that f of minus x is equal to f of x. So what happens here is that for odd functions, we see that they are symmetrical about the point of origin. So we kind of draw this diagonal line like this, okay? And we put this mirror along this diagonal line. So this portion is symmetrical about that portion. So odd functions are symmetrical about the point of origin. So they are symmetrical about the origin. So in terms of the trigonometric graphs, so we can have sine x. We'll just draw sine x quickly. Okay, so the sine graph looks something like that. Carries on and goes on like that, okay? So here we have minus pi over 2, because that's minus 1. And here we have pi over 2, sorry, that's 1, and that is pi over 2. So sine of 90 degrees or pi over 2 radians is 1, and sine of minus pi over 2 is minus 1. And you can see that we can draw our dotted line diagonal and if we put our mirror on the diagonal, we can see that we have something there and it's symmetrical about there. So those two kind of peaks are symmetrical about the origin. That's why it's an odd function. So numerically, we can write it that sine of minus pi over 2 is minus 1, whereas sine of pi over 2 is 1. So this indicates that it's an odd function because f of minus x is equal to minus f of x. So sorry, there should be a minus here. So we can have functions that are neither odd nor even. So an example of this could be something like we have some oscillation like this. We can see that this is neither, it's not symmetrical about the y-axis, neither is it symmetrical about the point of origin, okay? So what we see here, we don't see on this side here. Neither is it symmetrical about, so this is neither odd nor even. Another example of a graph that is neither odd nor even would be something like maybe a straight line, something like that. Y is equal to 2x plus 3. So we can see that it's not symmetrical about the y-axis, nor is it symmetrical about the point of origin. So we also now want to look at what happens when we take the product of odd and even functions. So this is very important now to understand the implications to the Fourier series. So if we have an even function, and if we multiply it by an even function, then what we get is an even function. So for example, we can have f of x equal to something like x squared, and then we can have g of x equal to cos x. So if we take f of x and we multiply it by g of x, then we get x squared cos x, and this is an even function. So the analogous to this is if we have a positive number and we multiply it by a positive number, then we get a positive number. So similarly, if we had an odd function and we multiply it by another odd function, then we get an even function. Analogous to this is if we have a negative number and multiply it by a negative number, then we have a positive number. And lastly, if we had an odd function and multiply it by an even function, then we get an odd function. So analogously, negative number multiplied by a positive number will give a negative number. So this affects our work with the Fourier series, and we can illustrate that with some examples. But before that, let's just analyze what even and odd functions do when we try to integrate them. We can take a function. So this would be an even function. And we're integrating from minus pi to pi. And we're saying that f of x is an even function. It's even because it is symmetrical about the y-axis. So if we were to integrate between minus pi and pi, f of x dx, then what we see here is that we have a certain area, okay, from 0 to pi, and it's exactly the same as the area from minus pi to 0. So all that we can do is we can integrate from 0 to pi f of x dx, and then just double it. It's just twice the area from 0 to pi. So that's an important implication of even functions. Conversely, if we look at odd functions, and if we look at something like that being an odd function, it's an odd function because it's symmetrical about the point of origin. And now we're integrating from minus pi to pi. And this year we're saying that f of x is an odd function. So in this instance here, if we integrate from minus pi to pi, f of x dx, well, we're going to have a positive area here, okay? And that is going to be counteracted by a negative area here. So the area here will be a positive number, here it'll be a negative number. The positive and the negative will just cancel each other out, and they'll be exactly the same. So this area will be 0. So if we had an odd function and we integrate the odd function between minus pi and 0, we're going to get 0. So what does all of this mean in terms of the Fourier series? What it means, firstly, if we consider f of x being an even function. So f of x is an even function. So we will remember that a naught is equal to the integral, okay, 1 over pi times the integral from minus pi to pi f of x dx. And since it's an even function that we're considering, we know that we can just integrate from 0 to pi and just double it, as we had shown in the graph just now. So this is the integral from 0 to pi. We multiply it by 2 and f of x dx. Then we can look at an. So an, same story, we have 1 over pi. We have integral from minus pi to pi of f of x cos nx. So what we have here, since we said that f of x is an even function, we have an even function and we are multiplying it by cos nx. And you'll remember earlier, we said that cos is an even function, okay? So we have an even function and we're multiplying it by an even function. So we're going to get an even function. So this entire product is an even function, okay? And since it's an even function, we can just double it as we had done with a naught. So we had 2 over pi times the integral from 0 to pi f of x cos nx. So that's a naught, that's an, and then lastly, bn. So bn, we'll remember, is 1 over pi, integral from minus pi to pi of f of x sine nx. So here we have an even function. That's what we said. We said f of x, we're saying it's an even function that we're considering. And we're now multiplying it by sine. Sine, you'll remember, is an odd function, which we had shown earlier. So just to refresh your memory, we can go all the way back up. You'll see that we said there's cos. We said cos was an even function. And there here we had said that sine was an odd function. Okay? And here we had spoke about the multiplication of the various types of function. And here we said an odd function times an even function will give us an odd function. So now we have an even function multiplied by an odd function. So that's going to give us an odd function. So this entire integral is an odd function. But what happens when we integrate an odd function? So when we integrate an odd function from minus pi to pi, we see that it gives us 0. Okay? So this odd function integrated between minus pi and pi is going to give us 0. So what does this mean? This means that if we identify f of x as an even function, we don't even need to bother to determine Bn. Simply by just being an even function, all of the terms associated with Bn is going to be 0. Therefore, we have an important fact that we must remember. And that important fact is that if f of x is an even function, then what it means is that the Fourier series will have only cos terms. So that means we only have to determine an. And we can do it with this simplified expression that we have shown here. So that's the first important fact. And this is considering that f of x is an even function. So we just want to do the opposite as well. We want to consider f of x being an odd function. So we have f of x being an odd function. So if f of x is an odd function, then what we're going to have is an as before equal to 1 over pi, integral from minus pi to pi, f of x cos nx. So here we are saying that f of x is odd, and cos nx we know is an even function. So the product of this odd and even function means that it is going to be an odd function. This entire thing is an odd function. So if we're integrating this odd function between minus pi and pi, it is going to be 0, as we had shown just now. So that means that if we identify f of x as an odd function, it means that we don't even need to bother determining an, because it's just going to be 0. We only need to determine bn. And bn is 1 over pi, integral from minus pi to pi of f of x sine nx. So we know that we can just integrate from 0 to pi, since this is an odd function, which is what we are defining it. And sine is also an odd function. So this entire thing is an even function. So that means that we're just going to have 2 over pi times the integral from 0 to pi of f of x sine nx dx. So the first fact that we had seen was that if f of x is even, then the Fourier series will have only cos terms. So the second fact that we want to write here is that if f of x is odd, then it means that the Fourier series will have only sine terms. So let's just refresh what the Fourier series is. So we have a naught over 2 plus infinite sum that starts from 1, goes the way to infinity, an cos nx plus bn sine nx. So if f of x is even, then we won't have this bn terms, we'll only have cos terms. That's what we had said, we had written it down. So if f of x is even, we'll only have cos terms because bn will equal to 0. So that's what we are saying here. So if f of x is even, then bn will equal to 0, and we'll only have this cos terms. So similarly, if f of x is odd, then an is going to be 0, and we will only have bn, and the series will only contain sine terms. So those are two important facts. So they simplify our work quite considerably. We don't need to write integrals for two coefficients if we can identify if the function is odd or even. So the third fact that we should just take note of, if f of x is neither odd nor even, then the Fourier series will contain both sine and cosine terms. So these three facts are the most important thing to remember about even and odd functions. So if we see that f of x is neither odd nor even, then we have to find both an and bn because they will be cos and sine terms. So we can just remember one of the examples we had done in the previous videos. Can go back and actually have a look at it. It was along the lines of so we had a function between minus pi and pi over 2. It took on the value 0, and then it went up to a value of 4, and it carried on like that. So this was minus pi over 2, and that was pi, and this was pi over 2, and that was pi. So if we write the Fourier series for this, and that was 4. So if we were to write the Fourier series for this, then we would remember that from the previous video, I think this was the first Fourier series that we had written. So you can look back at the video where we determined the Fourier coefficients and did the first example. So this was that first example. So we had shown in that video that f of x is equal to 2 plus 8 over pi cos x minus 1 over 3 cos 3x plus 1 over 5 cos 5x, and so on. So if we look at this function, we can just ask ourselves, is this an odd or even function? Well, we know that even functions are symmetrical about the y-axis. Okay, if we put a mirror on the y-axis, what we'll see on the left-hand side, we'll see on the right-hand side. And what did we say now in terms of our facts that we had written? So the first fact that we had seen was that for even functions, if f of x is even, we will have only cos terms. So we only need to evaluate the coefficient an. And if we look back at the first Fourier series that we had written, then you can see that we only have cos terms. And since this is an even function, we only have coefficients for an. So that first example, if we had known this when we had did that example, it would have simplified our work a great deal, because we would have known that we only need to determine an. We would not need to have evaluate bn, evaluate another integral, and all of those things. So this is the advantage of knowing this. So just to summarize once more, we have to identify even and odd functions. We said that even functions are symmetrical about the y-axis. Odd functions are symmetrical about the point of origin. We looked at products of even and odd functions. Product of even and even was even, and so on like that. And then we had looked at integrals of even and odd functions. And then lastly, we put that into context in the Fourier series and saw that if we identify if a function is even and odd or neither, then we can actually simplify our work by only determining one of the Fourier coefficients. So thank you very much for watching.